Okay, everyone, welcome back to part 2 of our CSEC Physics Paper 1 session. We are working through the specimen paper that CXC provided us, and this is from the year June 2012, okay? So we're at item 31, which refers to this diagram here, right? And so looking at the diagram, we can see that there's an air-paraffin interface here, and we have the ray of light passing from the paraffin into air where it's refracted, and that angle of refraction is given by X degrees, and the angle of incidence, right, that air paraffin boundary is 28 degrees, okay? So the question reads then, a ray of light passes from paraffin into air, so this is the direction of the ray. It passes from paraffin into air at an angle of incidence 28 degrees. And so they're saying now, if the refractive index of paraffin is 1.44, we need to find the value of sine X, which is our angle of refraction, okay? So we're gonna apply Snell's law in writing out our formula that we're gonna need to use to find the value of sine X, so the value of this angle of refraction, okay? Okay, so to do that, right, you see here that we're going from a more dense medium, which is paraffin, because its refractive index is 1.44. So we're going from paraffin, and then we're going to air, which has a refractive index of 1, right? So because air is our second medium, we're going from paraffin to air. Air is our second medium. So we're going to write the refractive index of air over the refractive index of paraffin, which is the medium that we're coming from, or our first medium, right? Medium 1. Then, okay, so let's just say, let's write it this way. So let's say, so this is our medium 2, because that's where we're going, and medium 1 is where we're coming from, right? So when we normally write Snell's law, we write it so that we write the refractive index in our second medium over the refractive index in our first medium is equal to the sine of the angle of incidence, which in this case is 28, right, over the sine of the angle of refraction, which is X in this case, right? So that's literally what I have down here, what I've written down here, except now I've substituted in my air because air is my second medium. So this is N of air, refractive index of air, over the refractive index of medium 1, which is paraffin. And that's equal to sine of I, which is sine of 28 over sine of X, right? So then sine of X will be equal to, if I'm transposing, because I'm solving for sine of X, right? So I do sine of X is then going to be equal to NP times sine I. So that's what I have here. And then divide that by air so that we can get sine X. And when we do that, we come down here and we say sine X is equal to sine of I, which is sine 28 times 1.44, which is the refractive index of paraffin, divided by the refractive index of air, which is 1. And so when I do that, I look among my answers to see if anything matches this, right? And when I look among my answers, I see that this one, B, looks like what I calculated. So B is our answer for 31. Okay? So again, this question relies on your recollection, your ability to remember Snell's law, and remember how it's actually defined, right? That is the refractive index of the second medium that you're going in over the refractive index of the first medium, the one that you're leaving from, and then everything is good from there on out, okay? From there, it's just a matter of transposing to make sine X your subject, and you'd get an answer here. And in this particular case, we got B, okay? So moving right along to 32, so item 32 refers to the following diagram. So here's our diagram here. We see that in the first figure, we have, what is this? We have a concave lens, and we have a ray coming in parallel to the lens, and then it's just been diverged, right? So it's diverging outwards, and then in this case, it's converging, right? And in this case, the parallel ray is going through the optical center and it's just going through undeviated, right? So they're asking us for 32, which shows a ray of light passing through a diverging lens, right? A diverging lens. So we want to pick the ones that show divergence, right? So the one that shows divergence is this one. So this first one, so I shows divergence because the parallel ray coming in diverges outward. And then in this particular case, this figure is all encompassing. It could go for a diverging lens or a converging lens because this is a key property of lenses in general, is that whenever a ray goes directly through the optical center, it's gonna be undeviated. So that's whether or not it's a diverging lens, this is gonna be true. So this is also a true figure for a diverging lens. It's true for a diverging and a converging. It's true in general. So this is an accurate figure as well as I. And so we select I and 3 for our answer, I and 3 only. So our answer here is C, right? 2 doesn't work because 2 shows convergence and we want to show divergence or a non-deviation through the optical center. So 1 and 3, we're good to go. So that's C for 32. So then moving along to 33 now. 33 says that the refractive index for light traveling from air to glass is, remember now, this is gonna be our first medium, medium 1, and this is our second medium, right? So when we write Snell's law that deals with refractive indices, we're gonna put our refractive index of glass on top, and then a refractive index of air on bottom. So that's what I did here. Refractive index of glass on top, refractive index of air on the bottom. And then now I'm gonna write it in terms of speed of light, because they're asking in terms of speed or wavelength or frequency. So I know I need to use my wave equation, right? Which is C is equal to F lambda. So ordinarily, we know that the refractive index of glass over the refractive index of air would also be equal to the wavelength of air over the wavelength of glass, or the speed of air over the speed of glass, right? Remember, these are inverted to the refractive indices. So if I'm writing NG up top, N of glass up top, I'm gonna write lambda of A up top and the speed of A up top. That's just how Snell's law, the rearrangement works, okay? So I know that C is equal to F, speed is equal to F lambda. So I can literally drop in a F here, and that would essentially make this all equal to speed, right? So they're asking us to pick which one of these represents the refractive index for light traveling from air to glass. So when we look at this, what do we see? We see speed of light in glass over speed of light in air. Do we see that here? No, we have speed of light in air over speed of air in glass. So this is not gonna work. So this is not correct. Wavelength of light in air over wavelength of light in glass. We see that here, right? We have wavelength of light in air over wavelength of light in glass. So this could work, 2 could work. And then 3 now, frequency of light in air over frequency of light in glass. No, guys, this is 1 because the frequency of light doesn't change based on the medium. It's gonna be the same always. And so I could effectively cancel these out. So that goes away to 1. So this isn't really a value. This is not gonna give us a value of our refractive index simply because the frequency of light in air and the frequency of light in glass are exactly the same. So this one doesn't work. So the only thing that works, guys, is 2. 2 only. So our answer for 33 is gonna be A. Okay? So our answer for 33 is A. So just remember Snell's law and remember what it represents and remember your wave equation, and then you'll always be able to do these kinds of analyses, okay? All right, so moving to question 34. Question 34 is based on this diagram here, right? So we're looking at a diagram here, and we see that it's a convex lens, a converging lens. We see the optical center here at the center. We see that we have a principal focus here, and we have 2F, twice times different principal focus out here, right? And of course, we have our parallel line here, our principal axis, right? All right. From the diagram above, a real image is produced with a converging lens when the object is located where, right? So that's the question. When does a converging lens produce a real image? Where does the object have to be for that to be the case? Well, what we do know about converging lens is that converging lens, these kinds of lenses are always going to give us a real image, except when the object is between the focus and the optical center. So if I were to put the object here, right, only in this case, will I get a virtual image and upright. So virtual and upright image is only possible from a converging lens when you put the object between the focus and the lens itself. And so in this case, the converging lens would act as a magnifying glass, right? So that's what happens in that case when we have the object between the focus and the lens itself. Now, all other cases, guys, every other case, if we put the object out here from F to infinity, anywhere we put it from F to infinity, as long as it's back here, we're always gonna get a real and inverted image, always with a converging lens, right? So this is the only exception. So let's see what the answers are here that we have to choose from. It says where, when the object is located, where will we get a real image? Well, between F and infinity, right? So that's what we're saying, is that whenever we are from F to infinity, we're always gonna get a real image. The only time we're gonna get a virtual is when we're here between F and the optical center, okay? So our answer here is C. Between F and infinity, we always get a real and inverted image from our converging lens, okay? So C for 34. All right, so 35 now, they're asking us about Young's double slit experiment. And you might remember that Young's double slit experiment was done to just kind of show the wave-like properties of light. And so really the key takeaway from Young's double slit experiment was about interference patterns that we're seeing, right? Regions of constructive interference and regions of destructive interference. So when it is conducted, what is it expected to show? Right? It's expected to show interference patterns on a screen. That's the whole point of the Young's double slit experiment. And that's what we get out of it, interference patterns on a screen. So we're gonna see regions of bright fringes and regions of dark fringes, and those are called interference patterns, okay? So our answer for 35 then is D. And so moving along, 36 is asking us about sound waves, and more specifically, the parameters of pitch and loudness. So they're saying pitch and loudness refer respectively to, is it amplitude and frequency? Is it frequency and amplitude? Or is it wavelength and speed? Or is it speed and wavelength? So they're just kind of like flipping things around, trying to throw us off. But we know that when we talk about pitch, right, the only thing that changes the pitch of a sound is the frequency. So if we change the frequency of the sound wave, we're going to change the pitch. And if we change the amplitude, we're going to change the loudness or the volume of that sound, okay? So amplitude is related to loudness and frequency is related to pitch, right? So let's see, that's B here, right? So they say respectively. So the first one matches with frequency. The second one, loudness, is related to amplitude. So our answer for 36 is B, right? So going right along now, moving along to item 37. So item 37 refers to the following diagram. So what we see in this diagram is we see a young lady standing here, right? We see a vase here on this table here. And the figure is showing us that the distance between the young lady and the vase is 0.5 meters. And then there's a mirror down here. And the distance between the young lady and the mirror is 5 meters, right? So the distance then between the vase and the mirror will be 4.5 then, right? Do you see that? The 5 minus 0.5, so that's 4.5 meters, right? Okay. So the question reads that there's a young lady here facing a plane mirror. So she's facing the mirror, which is 5 meters away from her, right? She views the image of a vase which is 0.5 meters in front of her. How far from her is the image of the vase, right? So she's standing here, the vase is like literally right here, the actual object is right here. And so she can see that in the mirror, but the question is asking us how far from her is the actual image, right? And so this question is leaning on our understanding of the properties of images that are formed in a plane mirror, right? And that property is here, right? That property is what I've written down here. That's the key property that this question is testing us on. And that's the property that the image that's formed in a plane mirror is going to be the same distance perpendicularly behind the mirror, right? Behind the mirror as the object is in front of the mirror. So this object here is 4.5 meters in front of the mirror. So the image that's formed is going to be 4.5 behind the mirror, right? So it's going to be somewhere out here, assuming that this is 4.5, our object would be somewhere out here, right? So the question is saying how far from the girl, though, is the image. Sorry, this is the image out here, right? The image is formed at the same distance perpendicularly behind the mirror as it is in front of the mirror. So this is our image out here, and this is our object here, which is the vase, right? But the question wants to know how far the image is from the young lady. So from the mirror, right, behind the mirror, the image is 4.5 meters. To get to the actual object, it would be 9 meters, and then to get to the young lady, it would be 9.5, right? So the answer here is D, which is 9.5. And we are moving right along, okay? So question 38 now says a transmitter emits radio waves of frequency 750 kilohertz. If the velocity of electromagnetic waves is 3 times 10 to the 8, which a radio wave is, it's an electromagnetic wave, so it's traveling at this velocity of 3 times 10 to the 8 meters per second, what is the wavelength of the transmission? So right away, we see that we're given the speed of light and we're given a frequency, so we can use the wave equation, which is C is equal to F lambda to calculate lambda. So we just rearrange, making lambda the subject and plug in the numbers that we have, right? So the question gave us the speed of light as 3 times 10 to the 8, and that the frequency of the radio wave is 750 kilohertz. So we write that down here. And when we plug that number in, let me plug that number in and see what I get. So when I plug that number in my calculator, what I get out is 400. So C is our answer here, right? So this is 400 meters, right? So 38 is C, right? So we just use our wave equation to rearrange for lambda and we get this number, okay? So moving along to question 39. So item 39 refers to the following diagram, which shows 2 resistors, right? There's R1, which is 6 ohms, and then there's R2, which is 4 ohms, 4.0 ohms. So the question is asking us what is the current in R1 if the current in R2 is 1.8 amperes. So if we look at the diagram now, we can see that we have current, the total current flowing through the circuit. Then once it gets to this junction, it's gonna break up, and then 1.8 of it is gonna flow through this part of the circuit. And then of course, the remainder will be flowing up here, right? In this part of the circuit. So that's what they want us to find out, this current here. That's what we're finding. We're finding this current that flows through the through R1. So in order to do that, we have to remember a few things here, right? So whenever we have 2 resistors in parallel, the voltage is gonna be the same that goes through both of them, right? So the voltage that goes through here, through this one, is the same as the voltage that goes through here because they're in parallel, right? So voltage will be the same, and then the current, of course, is gonna be different, right? So what we can do is we can look at this part of the circuit, so this bottom part, and using these values of current 1.8 and resistance of 4.0, we can calculate the voltage down here and just know that whatever voltage we get down here is going to be the exact same up here. So if you follow me over here, I did just that here. So V is equal to I times R. So if we want to find what the voltage is down here, all we have to do is do 1.8, right? So we do 1.8 amperes. That's what I have here, times that resistance, and that would give us a voltage in the bottom circuit, the bottom portion of the circuit. That would give us 7.2 volts. So if down here, the volts is 7.2 volts, and we say that they're in parallel, these two resistors, then the volts up here will also be 7.2 volts, right? And so remember, what we want to find ultimately is the current up here. So all we have to do is plug in this number of volts in, so V is equal to I times R. And so because we want to find current, we make current the subject. So we end up doing I is equal to V over R. And we just found that that V is 7.2. So if you follow me over here, what we're effectively doing is saying, okay, 7.2 divided by this resistance here will give us our current flowing through this resistor, and that turns out to be 1.2 amperes. So we're gonna look in our answers now, and the answer is A, because that's what we calculated, that the current is 1.2 that's going through this resistor. But the key thing to remember here, guys, is that whenever you have two resistors in parallel, they'll have the same voltage across them. The exact same voltage across one will be the voltage across the other. And the only thing that's different is the current that's flowing through them, okay? So that was the key pointer here, the key point to remember. Okay, so looking at question 40 now. Question 40 says that a transformer was connected to a 100 volt supply. So that's the primary voltage. And then the output measured was found to be 10 volts. So the output voltage in the secondary coil would be 10 volts. And then the output current, so IS in the secondary coil would be 0.5 amperes, right? So they're asking us to calculate the primary current, or IP, right? This is what they want us to find, IP. And so we know there are several relationships that we can use for transformers. And one of them I've written here that relates the voltage in the primary coil over the voltage in the secondary coil, and so that that's equal to the current in the secondary coil over the current in the primary coil, right? So since we want to find IP, which is the current in our primary coil, we just rearrange, making the current in the primary coil our subject, and then we just plug in these values because we know all of these, right? We know that the voltage in the secondary coil is 10 volts, so we plug that in here. We know the current in the secondary coil is 0.5, so we plug that in here. And we know the voltage of the primary coil was 100. That's what we started with, okay? So when we do that now, we come out with the IP, the primary current, being 0.05 amperes. So we look for that among our answers, and that is B, okay? So our answer for 40 is B. All right, so moving right along to item 41 now. So item 41 refers to this truth table that they're showing below. So we have our inputs A and B and our outputs C, right? So let's look at this truth table, 0, 0, 1, 0, 1, 1, and then 101, and then 110, right? So the logic gate that gives the above output is what? Like which logic gate, which one of these logic gates would give us this output? So what we want to do first is we want to look at, say, okay, if it was an OR gate, let's pick this one, right? If we had an OR gate and one of our inputs was 0 and one was 1, then what would the output be? Yeah, the output would be 1 in that case because it's an OR gate. So maybe an OR gate might work. Let's try another set of inputs for our OR gate though. 0 and 0 in an OR gate would give us what? It would give us 0, right? So 0, 0 in an OR gate would give us 0 because we need at least one to be, we need at least one of the inputs to be 1 in order to get 1. So this wouldn't work for our OR gate actually. So OR gate is not our answer, right? Because these sets of input don't match the set that we get from the examiner. So if we look at an AND gate now, in an AND gate, if we have 0, 0, what would we get? We would get 0. So we know that an AND gate is not our answer because in the question, they told us that this particular logic gate is gonna do 0, 0, 1, and an AND gate would do 0, 0, 0. So we know that this is wrong. can be our answer. So let's look at a NOR gate now. So a NOR gate is literally the opposite of the OR, right? Inverted OR. So in our OR gate case, whenever we had a 0, 0, we would have gotten a 0. But in this case, because it's a NOR gate, we're gonna get a 1. It's gonna invert the output, right? So would I get a 1 if it was a NOR gate? And we see that that matches this first row of the truth table that the examiner gave us. So let's look at the second one. If we had a NOR gate and we had 0 and 1 as our input, what would we get? We would get, if it were an OR gate, we would have gotten what? We would have gotten 1, but because it's a NOR gate, we should get 0. And we see that that doesn't match with what the table gave us. The table showed us that whenever we put in 0 and 1, we should get 1. But in a NOR gate, if this were a NOR gate, we would have gotten a 0, right? So this is not it. So that leaves us with the NAND gate, right? That leaves us with the NAND gate as our only option, but let's just test to be sure. For a NAND gate, is not an AND, so it's an inverted AND gate, right? In an AND gate, what did we have? If we have 0, 0, we would get 0 in an AND gate. So in a NAND gate, if we have 0, 0, we should get 1. So already we're doing well. We match this first row of the truth table here. If we had 0 and 1 in an AND gate, that would give us 0, but in a NAND gate, it's gonna give us 1. And so we see that that matches here, right? If we had 1 and 0 in an AND gate, that would give us 0. But because it's a NAND gate, we're gonna get 1. And so we see that that matches here. And so now let's look at 1, 1. If it was an AND gate and we had 1, 1, we would get 1. But because it's a NAND gate, we're gonna get 0. Okay, and we see that that matches here. So our answer for 41 is D. Okay, NAND gate. This truth table matches that of a NAND gate. Okay, so 41 is D. Moving along to 42. So 42 says if in a transformer, the number of turns on the secondary coil is greater than the number of turns on the primary coil, then what kind of transformer do we have, right? In that case, so this is kind of how I just drew a little schematic. So if our secondary turns are greater than our primary turn, what do we have? We have this kind of setup where we have all these turns over here, right? And so we're gonna get a greater induced EMF on this side because our turns are much more than what we started with. And so in this case, we would say it's a step-up transformer. It's gonna step up our voltage, right, from what we put in. So if we put in 10 volts, we can get 100 volts, right? Just for argument's sake. But whatever we put in, we're gonna get out something bigger than it because our secondary coil has far more turns and it's gonna be able to induce an even greater EMF, right? So yeah, so that's what we end up with, this being a step-up transformer. So our answer for 42 is gonna be B. Okay? All right. So that's just some transformer theory for you. So for question 43, it asks, which of the following quantities is constant in a parallel circuit? So you might remember up here, we just kind of looked at a parallel circuit where we had this kind of setup, right? This is a parallel circuit where we have like these two resistors in parallel. And remember what we had said was constant is the voltage, right? So the voltage throughout the parallel cell is gonna be constant while the current changes, right? So let's go back down here. It's the exact same thing. It's asking us to kind of use that knowledge. If we have a parallel circuit, our voltage across the components will be the same, right? So the answer for 43 is B, right? So moving down to question 44 now, it says that a magnetic field can be used to deflect the path of which of these radiation or which of these rays. So let's think about it. In order for a magnetic field to deflect anything, right, the thing, right, or that ray has to have a charge, right? So the thing must have a charge, ray must have a charge. The ray or the particle that we're looking at must have a charge. in order for it to be deflected. If it doesn't have a charge, it's gonna be undeflected, right? So when we look at our answers, what we're looking for is something that has a charge. Any kind of charge. It can be a positive charge or a negative charge, but it has to have a charge in order to be deflected in a magnetic field. And so we look at beta rays. We know that beta rays are negative. They have a negative charge on them. So these might work, right? These are gamma rays. Gamma rays have 0 charge. X-rays don't have any charge, and light rays don't have any charge. So our only possible answer here are beta rays, right? Beta rays or beta particles are negatively charged. They are often likened to electrons. And so our answer for 44 then is going to be A. Okay, so 44 is A. Moving down to 45 now. 45 says, which of the following scientists discovered the relationship E is equal to mc squared? Now we know that this is Einstein's relativity equation, right? Or mass equivalence equation. So this is from Einstein. Einstein was the one who did this kind of work, okay? So our answer for 45 then is C, right? That's Einstein's relativity equation. So this one is C, right? So 45 is C. So moving down to 46 now. 46 says, for any 2 consecutive elements in the periodic table, the first element has 1 less. All right, so let's just pick 2 random ones from our periodic table. Let's pick sodium, which is 2311, right? And then right after that one, we would have 24 magnesium, right? So let's just pick those 2 and look at what's less in the one case. So this is our first element and this is our second element. What is this? What is less in this than this? Well, the periodic table is arranged in order of protons, right? In proton numbers. And so when we go from sodium to magnesium, what we see is that the proton number increases. So that means that the first element is 1 proton less than the other one, the one that follows it, okay? So we have 1 proton less in sodium than we do in magnesium, so our answer is A. Okay, so 46 is A. Moving right along to 47. So 47 says a radioactive substance with a particular half-life, right? As time increases, so as time goes on, the radioactive substance, what happens to the radioactive substance? So remember what we say half-life is? Half-life is the time that it takes a radioactive substance to decrease to half of its initial value, right? And so that's a positive time, right? As time goes on, when you get to the half-life, you're gonna be half of what you originally had. And so as time then increases and progresses, the radioactive substance is gonna decrease, right? As it goes on with time, it's gonna decrease. And if we were to look at the activity curve, right? Whenever we plot these activity curves, so activity versus time, right? What we typically have is we see that there's like a, it kind of like asymptotes, it never really levels off. So we can't say it vanishes because the radioactive substance is never gonna completely vanish, but it would like gradually decrease, like decays like this, and then it just kind of levels off like an asymptote to the x-axis. So we can't say it vanishes. It doesn't vanish, but what it does is that it decreases over time, right? So as time increases, our activity or the mass of our radioactive substance is gonna just gradually decrease, okay? So our answer for 47 is C. So then moving on to 48. So 48 says, what did the Geiger-Marsden experiment establish as being present in the atom? So just a little quick refresher, the Geiger-Marsden experiment is also known as the Rutherford alpha scattering experiment. And what we got out of this was that there's a positively charged nucleus in an atom. That was a key takeaway from the Geiger-Marsden experiment, that there's a positively charged nucleus, right, that was able to kind of deflect some of those alpha particles and so on and so forth. So the key takeaway was about there being a nucleus and that nucleus was positively charged, right? And so among the answers then, what did it establish? It established the presence of a nucleus in an atom. right? That was the key takeaway from the Geiger-Marsden experiment. So our answer for 48 is B, right? So moving along to 49 now. So for 49, the atomic number and the mass number of an atom are 50 and 120 respectively. So the atomic number is the smaller one that we write down here, and the mass number is the larger one that we write up here. And this is just for arbitrary atom A, right? So what does this mean? When we say that the mass number is 120 and the atomic number is 50, what do we mean? We mean that this is the number of protons, right? So there are 50 protons in that. And if it's a neutral atom, there are also 50 electrons, right? So we have 50 electrons and we have 50 protons if it's a neutral atom. And then the number of neutrons, N, will be the mass number, 120 minus 50, right? So the number of neutrons will be 70. There'll be 70 neutrons in this nucleus. So let's see what they're giving us as options here. 120 protons, no, that's not true. As we said, we're gonna have 50 because this is the proton number. Neutrons, how many neutrons we're gonna have? 70, we calculated that, so this is wrong. Do we have 70 protons and 50 neutrons? No, that's wrong. Do we have 50 protons and then 70 neutrons? Yes, so we have 50 protons and we have 70 neutrons, so our answer is D. Okay, so moving on to question 50. Question 50 says that on Sunday, right, the corrected count rate of a radioactive source is 240 counts per second, right? So this is Sunday. So we're at Sunday. On Sunday, we have a count rate of 240 counts per second, right? Exactly 2 days later, the count rate had fallen to 120 counts per second. So 2 days later than Sunday is going to be what? Monday, Tuesday, right? So 2 days later is going to be Tuesday. And at Tuesday, the count rate fell to 120. So half-life. So the half-life is what? 2 days, right? So 2 days is the half-life, is the time that it takes for it to go to half of its initial value. So we go from 240 to 120 in 2 days, right? And then after exactly 4 days on Saturday, they want us to find out what the count rate would be. So let's continue along this path, right? Sunday, we go from Sunday, and 2 days later on Tuesday, we're at 120, right? And we establish that the half-life is 2 days. So 2 days from Tuesday would be what? 2 days from Tuesday would be Thursday. And we're going to fall to half of the 120 on Thursday. So that would be 160. So we're at 60 after 2 more days, right? So then now, 2 more days after this is going to get us to what? Saturday, which is what the question is asking us about. So 2 days later, right, we're going to end up at half of where we were on Thursday. And so on Saturday, then we'll end up with 30, right? Do you see that? So that's essentially 1, 2, 3 half-lives later, right? So in one half-life, we lost 120. In the second half-life, we lost 60. And in the third half-life, we lost 30. So that's 30, 60, and 120. So what's that? 30, 60, and 120. Yeah, so that would leave us with 30. Okay, so that's how we ended up at 30 here, right? So our answer for 50 is C. Okay, so moving along to question 51. So 51 is talking about charging a polythene rod by friction, right? So whenever we take a polythene rod and we rub it with a cloth, what's going to happen is that the electrons from the cloth are going to be transferred to the polythene rod, and we're going to end up with a net negative charge on the polythene rod. And because the cloth lost its electrons to the polythene rod, the cloth is going to end up having a net positive charge, okay? So we have to find the answer that matches that. When a polythene rod is rubbed with a cloth, it becomes, so the polythene rod becomes what? Positively charged? No. Positively charged by gaining? No. Negatively charged by losing electrons? No. It becomes negatively charged by gaining electrons from the cloth. So our answer for 51 is D. Okay, so that's just how it works, charging by friction. The cloth is going to give all of its electrons to the polythene rod, ends up having a net positive charge on the cloth, while the polythene rod that gained all of its electrons ends up being negative. So 51 is D. So now 52 is asking about a transformer. Again, remember we just did a question about this when they're asking us what would happen in a particular case. Now for a transformer in general, we use a transformer in an electric circuit to do what? To alter the voltage, right? So we can either step up or step down our voltage based on the number of turns that we have in our transformer, okay? That we start with and that we end with. So we're gonna use the transformer to alter our voltage in the circuit. Okay, so answer for 52 is A. Moving along now to 53. So 53 says, which of the following materials are conductors? Well, we know wood is not a conductor, that's an insulator. There are no free mobile charge particles that can conduct, right? So wood are not conductors. Gold is a metal, and we know that metals, right? Metals have positive ions in that sea of delocalized electrons. So metals can conduct and gold will be able to conduct. In graphite, we know that in the structure of graphite, there's a free electron per carbon, right? Every carbon in graphite has a free unbonded electron. And so graphite will be able to conduct. And so our answers here are 2 and 3. And so that's C. When we look among our answers here, that's C. So yeah, so 53 is C. Okay. All right, so moving on to 54 now. So 54 is asking us about Fleming's left-hand rule. It's associate a quantity with each finger shown in the diagram below. The correct order of the quantities labeled 1, 2, and 3 is, and we're gonna have to select the answer down here. But let's look at our fingers and see. Remember, with Fleming's left-hand rule, the first this thumb finger here is force or thrust, right? That's what our thumb represents. And then the first finger, our index finger, is gonna represent field. And then our second finger, right, or our middle finger represents current, right? So let's look down here and try to match force, field, and current. So it's not this one, it's not A, it's not B, it's not C, it's D, right? So we're matching force, field for the second one, and then current for the third. So that's this one, right? So our answer for 54 is D. All right, so moving along to question 55. So question 55 says that a student requires a circuit to measure the resistance of a resistor. Which of the following circuits is correctly connected, right? So what we're looking for, guys, like whenever we're trying to measure like a parameter of a particular component, we want to make sure that there's the ammeter that's in series with that component, right? So it's for the resistor that we want to measure its resistance. The ammeter is supposed to be in series with it, and then the voltmeter is supposed to be in parallel with the component that we want to measure. So in this case, we see that the voltmeter is in series with it. That's not what we want. And in this case, we have the voltmeter being in series with the resistor. Again, that's not what we want. In this case, we have the voltmeter being in parallel with the resistor, and the ammeter is in series with the resistor. So this is exactly what we want. So our answer is C here. Okay. All right. So this one wouldn't work because we have a switch in the middle, and then we have the A and the V down here. So this is not it, right? This is not it either. So C is our answer, right? Ammeter in series, voltmeter in parallel. And so C is our answer for 55. So 56 now, the item 56 refers to the following unit, the following circuit, right? So here we have, what do we have here? We have a lamp here, and then we have our power supply here, we have our cell here, then we have another lamp here, then we have an open switch and a lamp here. So this is R, T, lamp R, lamp T, and lamp Q. So they're saying in the circuit shown above, which lamps will be lit when the switch is closed. So when we close the switch, we're going from open to close, right? So what's gonna happen is that this part of the circuit is gonna be off by itself, And so this Q will not light. So no light is gonna be seen at Q, right? But because our lamp up here is in parallel with the cell, we're gonna see some light up here, and we're also gonna see light down here, right? So the current is gonna come, flow this way and flow this way, and we will see light in R and T only. Q won't light up, right? And so our answer is gonna be D, T and R. All right, so 56 is D. So moving along to 57. So item 57 refers to the following diagram, which shows a coil carrying a current and wrapped around a wooden cylinder, right? So this is our situation here. We have this coil that's carrying a current and it's wrapped around a wooden cylinder. We have this point X out here. We have a point Y in the middle, right? And we have this point Z out here, right? So the question is asking us which row of the table shows the magnetic field directions at the point X, Y, and Z. So we have to find out the direction of the magnetic field at all these points, right? So here's how we're gonna do that, guys. Because we have a current carrying coil, a coil carrying current, we can use Fleming's right-hand rule, right? And so if we use the right-hand rule, what we're gonna do is we're gonna take our 4 fingers and we're gonna just wrap them around that coil in the direction of the current. So in this particular case, we see that the current is going up and then coming over. So we're gonna curl our 4 fingers on our right hand. We're gonna curl those towards us and under. And wherever the thumb points, wherever the end of your thumb is, right? The tip of your thumb is gonna be where the North Pole is, right? So in that particular case, again, we're gonna take our fingers and we're gonna curl them over that wood or that coil. And so we're gonna come forward to ourselves and then point our thumb towards the right. And then the tip of that thumb will be our North Pole. So our North Pole will be here and our South Pole will be here, right? And we know how field lines run. The field lines run from north to south. And so what we're gonna get is that we're gonna have these lines, field lines coming out here and then coming around, right? Coming around from north to south, right? And so it would come this way as well, right? And this way as well. And then of course, it's gonna be coming out of here, right? It's gonna be going into here, right? So we're running from north to south, right? North to south, north to south, right? So you're coming into the south and you're coming out of the north. And so at the point X, right, the field lines, the field is gonna be going towards the right. So let's look for one that's going towards the right. So we can rule out this one. The Y, how are the field lines going? They're going to the left because they're coming from north to south. So they're going to the left. So let's see one that shows us that. Right, so these two show us that, so it's between these two. This one doesn't, so we can rule out D. So let's write it. So at X, we have something pointing to the right, the field pointing to the right. At Y, we have the field pointing to the left. And then at Z, we have it pointing to the right. So let's see what matches that. So we're supposed to have right, left, right. Right, so right, left, right would be B. Okay, so B is our answer for 57. So 57 is just really relying on our use of Fleming's right-hand rule, okay? So we have X going right, Y going left, Z going right. So that's this one, okay? So B is our answer for 57, and we just use Fleming's left-hand rule to come up with that. So that's 57, B, and then 58 now. Which of the following is not true when a magnet is moved relative to a coil, right? So we have our magnet and we have our coil, right? And so we can move it in and out, in and out, in and out. That's the basis of electromagnetic induction, right? We have a coil and then we have a magnet that's coming in and out, and that it induces an EMF in the coil, right? When we do that in and out motion. So which is not true about that electromagnetic induction situation. The greater of numbers in the coil, the smaller the induced EMF will be. That's not true, right? The greater the amount of coils that we have, more turns, right? More turns mean a stronger magnetic flux density, and so we'll be inducing an even greater EMF. So this is not true. Greater coils should always translate to a greater EMF. So this is wrong, right? So the faster the magnet moves relative to the coil, the greater the EMF. That's true. Because when we're moving the magnet fast, in and out, in and out, in and out, we're cutting those lines of flux in a very rapid way. And so that's actually it's the rate of change of the flux that's gonna induce the EMF. So if we move if we move the magnet really, really fast, back and forth, we're gonna induce a lot of EMF, okay? So this is correct. This is correct. And then the stronger the magnetic field, the greater the induced EMF. That's true, right? So this is true. So what's not true is this first one. So one only. So our answer for 58 is gonna be A. I only, that's not true, okay? So for 59 now, 59 refers to the diagram below. So we have these field lines going from A to B, right? And they're saying now in the electric field diagram above, the charges labeled A and B are, we know that when we're talking about an electric field, the field lines run from positive to negative, right? So because we see that all these field lines are coming out of A, we know that A has to be our positive charge. And because we see all these field lines coming in to B, we know that B has to be our negative center or our negative charge, okay? So then if we're supposed to choose which is A and which is B, then we said A is positive and B is negative. So then our answer for 59 is D, okay? And this is just really relying on our knowledge of field lines in an electric field and knowing that if it goes away from something, that charge is positive, and if it comes into something, it's a negative, okay? So 59 is D. And then finally, we're at question 60. So the radioactive decay of an isotope, radon, is given by this nuclear decay equation. So we have radon here, and we see that we're going to form polonium, which has a mass number of A, they wrote here, and B here. And that's formed from the emitting of a helium nucleus from radon, right? No, they're asking us to find the value of A and B, right? And so the way that we're going to approach this is we're going to say, okay, we know that whenever we have alpha decay, the mass number, which in this case was 220, so that's our mass number. The mass number is going to decrease by 4 because we're emitting a helium nuclei, so that's going to decrease by 4, and then we'll end up with A, right? The atomic number Z, which in this case is 86, is going to decrease by 2. So when that happens, Z minus 2, we're going to end up with this value of B here for polonium's atomic mass. And so, atomic number. And so when we do A minus 4, which is 220 minus 4, we're going to get 216 for here. So we're going to get 216 here. And then when we subtract 2 from radon, we're going to get 84, right? From down here, we're going to get B being 84. So let's look for the ones that match that. So we're looking for 216, 84. So that's not this one, it's this second one, right? So the key thing here to remember is that whenever a radioactive isotope emits alpha particle, the mass number is going to decrease by 4 and the atomic number decrease by 2. Okay? So that's it, guys. That was everything here on this paper. Thank you so much for hanging out with me. I would really appreciate if you like this video, if you share it with your friend, and if you subscribe to this channel. Lots of great content coming for you as you move forward in your physics career and your physics learning, okay? So thank you. Definitely subscribe, and I'll see you around, okay? All the best in your exam.